Morning, everybody. Welcome. I can see 239 of you on the call. I'm going to share my screen too, talk about what's going on today. Today we're continuing along with chapter 11. I'm going to finish off a couple of the questions and slides from last class because I'm a little bit behind. But we got 3 lectures this week, even though we're almost really done the material. So on Wednesday, I'm planning some course review and talking about the specifics of the final exam. I'll also give you more specific details about exactly what rubric to expect for the long answer question on the final exam. Because it's sort of chapter dependent, isn't it? I'm showing there a standing wave of sound in an open closed tube. The animation of that. Let me just make sure I've got my chat window open and my participants list. There it is. Okay. A minute while I get my Zoom windows all set up here. Okay. Sometimes it goes a little slow. So this is a really good question about if you have a conflict for the final assessment. I believe you're going to have to contact me about that. So Physics 131 fall, it actually goes to April Seeley, and we can try to figure out what to do about that. I don't think, normally in a normal year non-COVID, you would contact the exams office about exam conflicts, but I think this year it's the departments themselves that are going to be dealing with these. So we'll figure it out. And the final assessment again is on December 17th at 7 o'clock in the evening, Toronto time. Okay. All right. So let's start, actually not iClicker, but with a poll discussion. This used to be iClicker. Old slide, sorry about that. Let me start a poll. The question is, you've got 2 wave pulses on a string. They're approaching each other at speeds of 1 meter per second. So this is showing you t equals 0 seconds. What will the string look like at t equals 3 seconds, so 3 seconds later? A, B, C, or D? This is the principle of superposition. Hopefully you remember. Okay, give me another 10 seconds to choose one of these 4, and then I'll show you what I was thinking. Okay. And survey says, most people are saying C. So 81% of you voted for C. That was what I was looking for too. And in terms of how I did it, so the rectangle goes to the left 1, 2, 3 meters because it's 3 seconds later. So it would look like that if it was the only thing. And then I'm going to switch to red, and the triangle goes 1, 2, 3 to the right, 3 meters to the right. So it would look like that. And then what you do, so I've drawn like the right moving wave only in red, the left moving wave only in green, and then let's use black, for example, to do the sum. So the sum, we'll start it here, and then go up, because you're just adding this green curve to this red curve. And then when the red curve goes back down to 0, it goes like that. So it's going to go up like that's going to look like a little house. at that moment. And then the triangle will continue along towards the right, and the rectangle will continue along towards the left. They just pass through each other like ghosts, as they say. And then if the square wave, Rohit is asking, what if the square wave was upside down? That's a good question. So then, yeah, then it would look just like D. If you had the upside down square wave, it's really good. And so you see a little bit of destructive interference right at the exact moment T, at the position 4 meters. So destructive interference is always just when you have a positive and a negative amplitude adding, and so you get 0 for a moment. Okay. So I want to talk about standing waves. So we talked about this a little bit last time, and we saw it on that animation when I clamped the end and set one end to be oscillating. So what happens is you've got, if you have a sine wave, maybe you say in the middle, you oscillate a part of a string. So you got a string clamped at both ends. You oscillate it up and down with simple harmonic motion at the middle. Well, what will happen is there'll be 2 sort of sine waves actually going away from the center. They'll hit the ends and they'll reflect. The reflected waves will travel through each other. And you'll still be creating new standing waves at the middle. So what happens in the end is that you end up with multiple overlapping sine waves, half of them going to the right, half of them going to the left. And whenever you do that, you get what's called a standing wave. And it has a particular look to it. It has a whole bunch of math to it. You can use trig identities and things to figure it out. But if you add the cosine of t over t, so 2 pi t over t minus x over lambda was the wavelength. This is what's called, let's go to blue. This is, the minus sign means it's a wave traveling to the right. Sine wave traveling to the right because of the plus sign. And then this, sorry, because of the minus sign, when you have a plus sign, this is, you're adding a sine wave traveling to the left. Okay, so as x decreases, t increases, and so that for any particular point, like a crest, then this will stay the same. Whereas with this one, as x increases, t increases, and this difference remains the same, and you remain on a crest. When you add these two together, you can use some trig identities, and you can get y equals 2a times sine of 2 pi x times sine of 2 pi t. So what this is just simple harmonic motion. SHM. Sort of. I mean, we used cosine, but it's the same. Sine and cosine are the same function, really, just offset by a little bit. So you're looking at particles that obey simple harmonic motion. However, what we have now, instead of just a out front, a sine 2 pi t over t, we now have this big thing. This is what's called a position-dependent amplitude. So the amplitude depends on where you are on the string. So, and what's interesting is that both of these waves were traveling along. You had t minus x and t plus x. Now, when you combine them, the wave doesn't move. That's why it's called a standing wave. It goes up and down at any particular point, but it doesn't travel in either towards the left or towards the right. And I think I have an animation. Yeah, so the animation of what it really looks like is this red curve on the bottom. And then sometimes in the books, you see it sort of drawn like this. So you're drawing 1, 2, 3, 4, 5 different snapshot graphs, all kind of overlaid on top of each other, corresponding to 1, 2, 3, 4, 5 different moments of time. So there actually is a moment of time when the amplitude is 0 everywhere. And then it goes, when one goes up, one of these antinodes goes up. This is an antinode. the adjacent antinode goes down and vice versa. And then you have these little positions on the wave in which there's no oscillation ever at all. The amplitude at that position is 0. So these are called nodes. Node, node, node. Positions of 0 oscillation. So yeah, the amplitude, as we said in this equation before, someone was asking, Teresa was asking, isn't the amplitude the maximum? It is. The amplitude is the maximum oscillation at any particular point. So when sine of 2 pi lambda over x equals 0, then that's a 0 amplitude oscillation, meaning that that's a node. So that's where there is no oscillation at all. It just sits there. So, and just to recap, the reason that standing waves form is whenever you've got something driving simple harmonic motion and you've got a reflecting end or 2 reflecting ends. So you form what's called a cavity, a resonance cavity, where these waves go back and forth and reinforce each other. And so actually, I want to ask about the wavelength. So there is a wavelength of this wave, which is whenever it repeats. It's the wavelength of the underlying waves, but also you'd say it's the wavelength of the standing wave. So here's a poll question. Look at this standing wave. And again, it's drawn like most textbooks draw it. What do you think the wavelength of that standing wave is? 0.25 meters, 0.5 meters, 1 meter, or 2 meters? So it's sort of the distance over which the thing really repeats. 10 seconds. Okay, 3, 2, 1. So 62% of you are voting for 1 meter. So that's, I think that's exactly it. So what you have to remember is, I'll draw it maybe in red, is that at any particular time, the wave is doing this, right? And then later it goes straight, and then later it goes up and down. So the actual repetition is 2 times the distance between adjacent antinodes. Okay. I mean, it looked like 0.5, so B was sort of the next popular answer, but in fact, you have to do twice the distance between adjacent nodes to get the wavelength. So let's review what the principle of superposition is again. The idea with superposition is that at each moment of time, you add up all the compressions. This is for a sound wave. So this is what's called principle of superposition for sound waves in particular. So sound waves can be thought of as air pressure versus time. 1 ATM is called 1 atmosphere. Okay, I've spelt it wrong there, sorry. Which is it's equal to the ambient pressure in the environment, maybe the room that you're in. Well, what a sound wave is, it's either a compression or a rarefaction. So an increase, a local momentary increase in pressure, or a local momentary decrease in pressure above or below atmospheric. So the principle of superposition is if you have overlapping waves, you add up the compressions, subtract all the rarefactions, and you get the new pressure difference at that particular moment. And so what I'm trying to say is you can do this for a string or you can do this for a sound wave. If 2 waves are in phase, meaning that all their crests line up, the red crest lines up with the green crest here, and here, and here. Also, the troughs line up with each other. So what you're doing is these rarefactions add up. You just get a bigger wave, so twice the amplitude. Okay, so a louder sound if you had two waves that are in phase, two sine waves that are in phase. So that's called constructive. You can also get destructive if you have this red wave adding to a green wave and the crest lines up with the trough and this crest lines up with this trough, then at every point, they're going to cancel each other out. So all the compressions will line up with the refractions, and what you get is sort of silence. Get no sound at all. And then if they are not exactly in phase, they're still out of phase, but not exactly, then you get something in between. Here we have, it looks like they're out of phase here by maybe a quarter of a period or something, in which case this new wave is also a sine wave, as it turns out, but it looks like it has maybe about the same amplitude as either of the individual waves. So it's not twice the amplitude, it's not zero, but it's somewhere in between. Okay, so this is, I'm going to start talking about beats. I've sort of introduced this, and then we're going to do a quick demonstration on this. So imagine that you have a 220 hertz sound. So that's the frequency of the sound. It sort of sounds like this, boo, and then you've got another sound which is 221 hertz, and they're playing at the same time. And what we've plotted here is the first 0.1 seconds of time, so 1/10 of a second. So 220 hertz means that there's a compression, these subsequent compressions coming 220 times every second. Now, both these waves start off to be in phase. So this crest is lining up with this crest, same time. But after 1/10 of a second, what happens is you'll get 22 of these waves from the 220 hertz and 22.1 of these waves from this from the green wave. So they're not exactly in phase after it, but they almost are. So you basically just get a double amplitude. But what if we go a little further in time? What if we plot now the first half a second? Well, in the first half a second, what you get is you get 110 of these red oscillations. But you get 110.5 of the green oscillations. So if they started off in phase, then you'll get an extra half a wave of the green one. So this red one ends up at a maximum, the green one ends up at a minimum, and they cancel each other out. And then in between, they're just sort of out of phase. So what's happening is they go more and more out of phase. So red and green gradually go out of phase. That's what I would say. And so that eventually they actually destructively interfere. And then if you go even further, so a whole second, after a whole second, you would have 220 oscillations of one and 221 oscillations of the other. So actually they'd be in phase again because you've gone through an entire other period. So if you look at the first actually 2.5 seconds, it's a little hard to actually picture because you can't really plot 220 wiggles. It looks like like a solid color. But anyway, you get what are called beats. And then you could, for example, change if you played a 220 hertz and a 233 hertz, then it would actually be every 1/13 of a second. The red curve would have a certain number of oscillations, about 17, and the green curve would have 18, exactly one more oscillation. So every 13th of a second, this is delta t equals 1/13 seconds, then the thing comes back into phase again, and you get a loud and then soft, loud, soft, loud, soft, and that's what's called beating. So beats are periodic variations in the loudness of sound that is due to interference. It occurs when waves of similar but not equal frequencies are superposed. And it provides a comparison of the frequency. The frequency of the beats turns out to be equal to the difference between the frequencies of the two waves. So if you look backwards at this one, 233 F beat equals 233 minus 220 is 13 hertz. So 13 times per second, you get one of these beats. That's how it works. And actually, I think I have a demo for it. Let's escape out of this. I'll put a link to this online tone generator. Keep the link. So I have two Chrome windows open. This one and this one. What we can do is let's play what a 220 hertz sine wave sounds like. Can you hear it? And then we can actually play, let's play what a 201 sounds like. And it's also a sine wave. Let's do, oh, that's 201, sorry, wrong. I want to do 221. You can definitely hear that. Oops, not 221. Can you hear the difference between this one? Probably not. I can't hear the difference. But if we play them together, you get beats. So every 1 second, you'll hear it go up and down. Oh, you can, okay. There's actually a musician in the audience who says they can hear the difference between the 220, which I cannot, and the 221. So it's, you know, it must be a little higher. What about 222 hertz? Again, to me, these sound maybe a little different. We play them together. Now you can hear 2 beats per second. Someone's just requested that I do 225. Let's do it. Naomi, 225. So again, let's start the 220, play the 225. Okay, so that's 5 beats per second that you're hearing there. And then let's do the 13. That's another good one. Biabele suggesting 233, right? Which is actually, I think it's the next semitone up. 220 to 233 is, I think it's a flat and sharp. Can you hear that? B flat, yeah, I think so. Good. What if we do like 440? See if we can hear the beats. Just sounds smooth, right? In fact, it sounds like a harmony or something. So we're going to talk a little bit about harmonics, but let's keep going with this. So I can play around with that a little. We'll come back to it actually when we talk more about frequencies. One application of beats is you can tune a piano the old-fashioned way, which is that you have some known frequency that you want the string to vibrate at, and then if it's very close, you'll hear beats if you sound the piano key and your known frequency at the same time. What you want to do is tune the string until the beats goes away, until F1 and F2 are equal, and then the beat frequency is 0, and then you don't hear anything. So this is from this equation 11.9 from your textbook. A beat is a wave that results from the superposition of 2 waves that are about the same frequency. And then the F beat is the absolute value of F1 minus F2. So I think I have some poll questions like this. Want to try it? Let's do a couple poll questions that get a little tricky. Poll question. If you combine the sounds of 2 pure tones, one with a frequency of 440 hertz, as we just did, and the other with a frequency of 220 hertz, what do you get? So if you're paying attention there, you might know. Okay. Ah, Robert just pointed out this is a perfect octave. Absolutely correct. Somebody knows their intervals. Okay. So let's end this polling and then maybe 5 seconds. I haven't seen a result that is so close. 129 of you say the beats have 220 hertz, and 126 of you say you got a continuous sound that humans perceive to be two sounds at once. So maybe this is sort of a mathematical preference or something, but to me, physics is talking about what really happens in the real world. I guess you might try to say that there's 220 beats per second, but I don't really know exactly what that means. It's not really beats. For beats to happen, for beats to occur, the frequencies F1 and F2 must be pretty close. Certainly, if they're off by a factor of 2 of each other, it's not really beats. It's just a harmony. Or as Robert points out, it's a perfect octave. So that's a bit of a trick question. Let's do another one. So this one, could I define pretty close? Maybe within like 10% of each other. It's my canonical go-to number, close to 10%. Okay, you're tuning a piano. Here we go. The old-fashioned way. You're not using one of these tuners. And you want to make the frequency of an A key to be 440 hertz, which is A440. But you suspect it is out of tune. You have a reference sound source that you know for sure makes a pure tone of 440 hertz. When you sound the reference at the same time as the piano key, you hear 3 beats per second. So what's the actual frequency of the out of tune string? Is it 440, B 443, C 437, or D it's impossible to know with the information given? Just hear if it's sharp or flat. So Duncan suggests that we should just hear if it's sharp or flat, but I can't, so I'm assuming that you can't, but maybe you can. Yeah, one of the unfortunate things about these Zoom polls is that you can't take back your answer once you've answered. It'd be nice if you could vote multiple times. Ten seconds, please. Okay, and we'll do a real question after this. This turned out to be another trick question. This had to do with the absolute value. Remember that the F beat, which is here, is 3 hertz, okay, is equal to the absolute value of F1 minus F2. And F2 is equal to 440 hertz. What this means is that F1 equals either 437 or 443 hertz. You don't know if it's A or B. So I think the best answer there is just D. Sorry about that. Let's do a real question. So again, it's you are tuning a piano. You want to make the frequency at 440 hertz. You suspect it's out of tune. You have a reference sound source that you know for sure makes a pure tone of 440. When you sound the reference, you get 3 beats per second. So everything's the same so far for the first paragraph. Then you tighten the string on the piano, which you know raises the frequency of the A key a little bit, the string you don't know. When you sound the reference at the same time, now you hear 7 beats per second from just tightening it a little bit. So what is the new frequency of the out of tune piano key? Is it A 440, B 447, C 433, or D it's impossible to know with the information given? And remember that up until this part, you knew that it's either 437 hertz or 43 hertz. But you don't know which. This one's not a trick question. Sorry, Lily. I think it's... So give me another 10 seconds. I'll show you what I'm going for here. 3, 2, 1. Okay, you guys got it. So this is better. So I'm looking for 447. The idea here is just that, okay, you originally just knew it was either 437 or 443. It was either a little low, the frequency was either a little low or it's a little high. You knew it was off by 3 hertz, but you didn't know which way. Then you tightened the string, increasing the frequency, and you knew that it gets worse. That makes sense? Yeah. So as the frequency, to hold this pen the right way, as the frequency goes up, it gets worse. You actually want the frequencies to match, right? If you're trying to make them in tune. So you're trying to get the beats to get farther and farther apart, the beat frequency to go down and approach 0. Instead, you've got the beat frequency going up to 7 hertz. So if you increase the frequency and you get worse, that resolves the ambiguity. You must have started at 443 hertz. Because otherwise, if you were at 437 and you increased it a little bit, you would get closer to being in tune. So now you're getting further away from tune. So then once you get to 7 beats, then you know you got to be up at 447 hertz. Makes sense? I think we're getting back to standing waves now. I've got some more things I wanted to say about standing waves and how it's related to music, actually. This is back to the mathematics of standing waves. So we said before, we've got y now is some variable function of x times sine 2 pi t over t. This is a standing wave. And this a function is also a sine wave. We've got sine in both of these instead of sine and cos. So in this wave they formulated, the nodes occur at these integer multiples of lambda over 2. So for a string of fixed length L, the boundary conditions can be satisfied, meaning that they're forced nodes at the end, only if the wavelength is 2 times L over m, where m is some integer number. Okay. And v is the wave speed. On the string. So that actually is going to be v equals, I think it's going to be square root of f over mu. Because lambda times f equals v, then you get, if that's the wavelengths of particular standing waves, then you can solve it out for frequencies, v over lambda m. It's m times v over 2l, where again, the lowercase m is what's called the mode number. So m is what's called mode number. Some people call it the harmonic number as well. We'll talk more about that in a minute. And then the lowest allowed frequency is when m equals 1, and that's when you've got half a wavelength between the two ends. Okay. And then what it looks like is you can have the m equals 1, you can have m equals 2, and you can have m equals 3, you can have m equals 4, you can keep on showing more and more. Each mode numbered by the integer m has a unique wavelength and a unique frequency. Let's just ask a quick question here. I'm going to do a 30-second poll. Oh, there is 4. Okay. of what is the mode number of this particular standing wave. And this is not a trick question, just either 1, 2, 3, 4, or 5. 10 seconds, please. Okay. Good job. Survey says, well, 74% of people who voted in time were going for E, which is correct. So, and the trick here is you've got 1, 2, 3, 4, 5. You count the number of antinodes. To get M for a standing wave on the string. Okay. So a couple things to note. M is the number of antinodes on the standing wave on a string. The fundamental mode with M equals 1 has a wavelength which is 2 times the distance between the ends of the string. So you got that half wavelength that fits in between. The frequencies of the normal modes form a series. You've got M equals 1 is that frequency, fundamental frequency. M equals 2 is double that frequency. As Robert pointing out, that's called an octave. But then you've also got 3F1, 4F1, 5F1, 6F1. These are called the harmonics. So it's called a harmonic series when you just go up by integer multiples of this base frequency. And the difference in frequency between any two adjacent modes is equal to the fundamental frequency. F of M plus 1 minus F sub M. Okay. And below is just showing you a time exposure showing a photograph of the M equals 3 standing wave on a string. Let me just, another really quick poll here. So you guys, oh wait, that's, what did I want to do? Oh, I wanted to do an example actually. So this is a list of a whole bunch of different frequencies of the piano. So there's 88 keys on the piano, and they have all these different frequencies. And what's interesting is that every time you go up to the same letter, you actually double the frequency. So it's going up like this A0, the lowest key on the piano, has a frequency of 27.5 hertz. If you go to what's called A1, the 13th key, so it's actually 12 notes up, it's another A, it's at 55, which is exactly 2 times. And all the A's come out kind of to be integers actually. A4 is again 440 hertz. And it's true for all of them actually. If you look at, what can we see here? C3 is 130.8. If you double that, you'll get up to 261.6. So every kind of octave goes up by this factor of 2 in frequency, and that's how they set up the piano. It's sort of a interesting thing. Let's do a quick question here. A steel guitar string has a mass density of 0.1 kilograms per meter. So let's write that down. Mu equals 0.01 per meter. And is held at a tension, which we're going to call F, is equal to 100 newtons. And don't forget that V is equal to the square root of F over mu. What should be the effective length of the strings to produce the note E2? So you're looking for L. Okay. L equals the question mark, and you want note E2, which is, by the way, 82.4 hertz from an online table. So what we're going to do here is we're going to assume that the string is in the fundamental mode. M equals 1. So F1 is equal to, what was it again? It was, V over 2 times L. Okay. So that's, this is, yeah, equation, I think it's equation 11.11 from your text. It's F1 is equal to V divided by 2L. So L is equal to V over 2 times F1, which is equal to the square root of F over mu times 1 over 2 F1. So the length here is equal to the square root of 100 divided by 0.01, which is, I think, 10,000. Square root of 10,000 is 100. Times 1 over 2 times this frequency, which is 82.4. So you do have to get my calculator out. I got 0.6068. Basically, it's L is equal to 0.6 meters, which is, seems about right for a guitar string. That you can hold a guitar. Okay. So Atang asked a really good question. Why are we assuming the fundamental mode? Well, you have to assume a mode in order to use equation 11.11, right? So I assumed fundamental. If you had assumed that it was the second harmonic, you would get a different number for L. It's not a very good test question, is it? Because you should be told that. But when, sometimes you have to make these assumptions. And then, yeah, and Faison asked a good question. How did I get 82.4? All I did is I looked it up on a table, which you can get these online somewhere. Again, these are both things that you would be given on a real test. Yeah, this was the poll question I thought I was going to do. Quick one. So let's do a 30-second poll here. Question is, the frequency of the third harmonic of a string is A, 1/3 the frequency of the fundamental, B, equal to the frequency of the fundamental, C, 3 times the frequency of the fundamental, or D, 9 times the frequency of the fundamental. You just click on that one in 10 seconds and we'll keep going. Gotta play a little bit. Well, we can do one more demo. Let's end this. Yeah, most people, well, not most, but 69% is most for sure. 3 times the frequency of the fundamental. So hopefully you've got that. Is that F3 is equal to 3 times F1. Okay, because F little m is equal to m times V over 2 L. So if you put in a 1, you just get V over 2L. If you put in a 3, you get 3 V over 2L. That's the way it works. So another way of putting it is Fm is equal to m times F1. Okay, so I want to talk a little bit about sound. Your ears are able to detect sinusoidal sound waves with frequencies between about 20 and 20 hertz and 20,000 hertz. Low frequencies are perceived as low pitch bass notes, while high frequencies are heard as high pitch treble notes. If you go above 20 kilohertz, they're called ultrasonic frequencies. So someone was talking a little bit about, who was it? That your dog was freaking out. I can't remember who it was here. Yeah, it was Cheng Peng. So, okay, I'm going to do that thing again, the sound generator. But let's just look at one of them and see. Let's try just a whole bunch of different hertz. Let's try. Can you do one? Play. Yeah. Let's put a square wave. Can you hear it? 2 hertz, just ticking. 3. So what you're thinking of is that something would be vibrating at 5 hertz, 10 hertz, 15 hertz, 20 hertz. If you make a triangle wave, it looks, can't hear it again. Watching. Make it a sine wave. Can you hear it? I can't hear it. Maybe it's my speaker. Can you guys hear it now? Depends if you're wearing headphones. Let's try 40. Again, the speaker on my laptop is not really producing these. Let's do 60. Good. I'm just going to keep going up to 500 hertz, to 1,000. We just keep going. So you may want to adjust your volume in case I'm going to blow out your ears. Let's do 2,000. See, 3,000. Okay, most annoying sound in the world. 4,000. Oh, let's do 10,000. Ah. let's do 14,000. I can't really hear it. Again, I'm a little old, so I can't. There, I can hear 12,000. Yeah, I can't hear the 13,000. Oh my God, so sorry. This is driving you nuts. Just turn down the volume. 15,000. Can you guys hear that? Let's try 19,000. So sorry, everybody. Let's do 19,900, and then I swear I'll turn this off. Okay, I think you can't go up to 20,000. Okay, stopping. So thank you for that. Basic idea is that one interesting thing about your highest frequency sounds that you can hear is that humans can hear up to 20,000 hertz, but it is age dependent. As you get older, your eardrum actually loses some of its flexibility, and so it loses the sensitivity to the highest frequencies. But dogs, for example, have the ability to hear higher frequencies than humans, so you can have a dog whistle that is in the ultrasound. Your dog can hear it. I think that's pretty much all I wanted to talk about today. I'm going to continue on tomorrow. We're going to get into standing waves, not just on a string, but also in a tube of air. We have an example for that. This is on Wednesday. I want to come back. So let's review. I do also want to talk about Doppler effect. I'm going to finish up all of chapter 11 on Wednesday. We're going to be starting in on some course review, and I'll let you know exactly what to expect on the final assessment on December 17th, including I'm going to give you a short list of what chapters the 2 written questions might be from, and what just a review of what the rubric is for those particular chapters. So you're going to need to figure that out on the question and use the appropriate rubric. Wednesday is actually the last day of classes in the University of Toronto Arts and Science calendar. But then Thursday is listed as makeup day for Monday classes. So if you had any classes that were Mondays, had a Monday lecture, and you missed a lecture back on Thanksgiving, then some professors, including me, might offer a lecture on Thursday. And so, but again, I'm just going to be continuing with some course review, and I'll be right here in this Zoom call. I've asked Pius if he could set up a liquid nitrogen levitating train with superconductors. So I'm going to try that out and try to like levitate some stuff. Maybe we'll dip some flowers in the nitrogen and smash them, but we're going to have a little bit of fun, just sort of have a little blow off steam on Thursday morning from 11 to 12. And that is the real last class. And that is it from me. I'm going to stay on this call for another half an hour, but I'm going to turn off the record, and I'll see you guys on Wednesday.